Hello and welcome. Today, we're going to explore one of the most fundamental components in electronics, the inductor. As you can see at the top of our guide, an inductor is a passive electronic component. What this means is that it doesn't create energy, but it's incredibly good at storing it. Specifically, an inductor stores energy in its magnetic field whenever an electrical current flows through it. Let's look at what an inductor actually is. On the left, you see a real-world example of a common inductor, called a toroidal inductor. It's essentially a coil of copper wire wrapped around a core, in this case, a donut-shaped one. To understand its properties, let's break down the diagram of a typical inductor. It's made of a wire wound into a coil. Several key factors define an inductor. The number of turns, and this is simply how many times the wire is wrapped around. The length, L, the length of the coil itself. The cross-sectional area, this is the area of the circle at the end of the coil. And the core material, this is the substance inside the coil. It could be air, or a material like iron or ferrite, which can dramatically increase the inductor's effectiveness. All these factors together determine the strength of the inductor. Now, let's get to the core principle of how an inductor behaves. The voltage across an inductor is directly proportional to the rate of change of the current flowing through it. We write this as V is proportional to d/dt. Let's break that down. V is the voltage. The symbol d/dt looks complicated, but it simply means how fast is the current changing at any given instant. So, if the current is steady, there's no voltage. But if you try to change the current quickly, a large voltage appears. To turn this into an equation, we introduce a constant called L, which stands for inductance. This gives us the most important formula for an inductor, V equals L asterisk d/dt. In this formula, V is the instantaneous voltage across the inductor. L is the inductance, which is a measure of the inductor's strength. We measure it in a unit called the Henry. And d/dt is the instantaneous rate of current change. Now, let's go through the key properties of an inductor, one by one. 1. Stores energy in a magnetic field. This is its primary function. When current flows through the coil, a magnetic field is created and expands around it. The energy is stored within this field. 2. Opposes changes in current. This is the most crucial concept to understand. An inductor acts like it has inertia, but for electricity. It resists any sudden changes in the current flowing through it. If you try to increase the current, it pushes back. If you try to decrease it, it tries to keep the current flowing. It's important to note that it resists changes in current, not voltage. 3. Inductance, L. Inductance is the property that quantifies this opposition to current change. It's measured in henries, H. A higher inductance, say 10 henries, means the inductor will resist changes in current much more strongly than an inductor with a lower value, like 10 microhenries. 4. Voltage-current relationship. As we've already discussed, this is defined by the formula V equals L asterisk d/dt. This means the voltage that appears across an inductor is directly proportional to its inductance and how fast the current is changing. No change in current means no voltage. A rapid change in current means a large voltage. 5. Symbol. In circuit diagrams, you won't draw a detailed picture. Instead, you'll use the standard inductor symbol, which looks like a small coil of wire. When you see this in a schematic, you know it's an inductor. 6. Energy stored. We know an inductor stores energy, but how much? The formula for this is E equals 1/2 asterisk L asterisk I superscript 2. Here, E is the energy stored, in joules, L is the inductance, and I is the current flowing through it at that moment. Notice that the energy is proportional to the square of the current, so doubling the current quadruples the stored energy. 7. Made of coils of wire. This is its physical construction. A simple rule of thumb is that more coils, or more turns of the wire, generally results in a higher inductance. 8. Used in. Inductors are everywhere in electronics. Some common applications include transformers, where two coils are used to step voltage up or down. Filters, to block or pass specific frequencies. Power supplies, to smooth out a fluctuating DC voltage into a clean, stable one. Radio tuning circuits, to work with capacitors to select a specific radio frequency, allowing you to tune into your favorite station. 9. Passes DC, resists AC. This is a fantastic summary of an inductor's behavior. For DC, direct current, the current is constant. Since the current isn't changing, d/dt is 0, and the inductor acts just like a simple piece of wire with very low resistance. For AC, alternating current, the current is constantly changing direction and magnitude. The inductor fights this change every step of the way. The higher the frequency of the AC signal, the more the inductor resists it. This makes inductors excellent for blocking or slowing down high-frequency signals. So, to recap, an inductor is a coil of wire that stores energy in a magnetic field, and its defining characteristic is that it opposes any change in the current flowing through it. Thank you for watching. I hope this detailed look at the inductor has helped you understand this essential electronic component. See you in the next video.